So we are
so it's very exciting for all of us and hopefully for YouTube. So as organizers, we actually have a range, like a wide range. So, so first lecturer is Sally Dawson. So Sally is a senior scientist at Brookhaven National Lab. So Sally has made important contributions to theoretical studies of Higgs physics and collider physics, along with precision calculations for the Large Hadron Collider. So Sally has a very prominent career and received many awards, such as the Sakura Prize from APS in 2017. So as students, I suppose you all know among all her many important works, you should know the Higgs Hunter's Guide. So this document was actually written long before the Higgs discovery in 2012, but since it appears, it has been the reference that the defining reference like for students, postdocs who want to study the properties of the Higgs boson. So without further ado, let's welcome Sally.
Okay. Okay, thank you, and it's really a pleasure to be here and lecture at TASI. It's one of my favorite things to come and talk to students and talk about the Higgs boson and just talk about why I study physics. I've done many, many lectures on the Higgs, and it's always new. There's always something I learned, so I hope you'll ask me lots of questions. I have PowerPoint slides, which is bad because you talk too fast, but I'm short, so I can't write too much on the board. So it would really, really, really improve my lectures if you asked a lot of questions. I'm friendly. I like questions. Go ahead, ask me questions anytime. And in particular, if you find mistakes in my lecture notes, I hope there aren't any, but there always are, please tell me so I can try to make them better. So I'm going to start and talk about the Higgs, and I hope you all have stolen the Higgs Hunter's Guide from wherever you can get it on the web. If you need the 2 HDM Feynman rules, that's where they are. I don't know about the rest of the book, but the 2 HDM Feynman rules, they're all right. Okay. Yeah. My mic isn't on?
I don't hear it in the back.
Guys, is my mic on? Hey, AV guys?
I hear it on. Maybe it needs to be a little louder.
Maybe I need to be louder. See, that's what happens when you're the first.
Yeah.
Yep.
Unfortunately.
No, it's me. So I'll keep blathering before I start. So my notes are posted. And what I'm going to do, I posted the first set of notes, but I'll just organize each day with what I did that day and then put the next days on. So you can look ahead and see what I've got there. It's easier to not have to write down notes. So, am I good? Okay. So I'm going to talk about the Higgs boson and also electroweak theory. Do I have a pointer here? Is there a pointer? Oh. One more thing. But okay. So the plan of my talk is I'm going to talk about the basics of the Higgs boson and the basics of electroweak symmetry breaking. And this will be like kind of a nice exercise. You're probably all super good at Mathematica. And you can type this into some Mathematica code and go through it and get the W mass. And this is a really good thing to do, just, you know, to see that you understand it, see how all the factors of 2's and minus signs and all that stuff works out. And then after that, I'm going to talk about the properties of the Higgs and how we explore the Higgs boson properties. What is it that we know about the Higgs? And why am I still talking about it? Why don't we know everything? What do we need to know in the future? And then probably in my third lecture, I'll talk about models with more Higgs bosons. And my favorite models happen to be models with an extra scalar singlet and an extra Higgs doublet, but there are millions of models. And these two models will sort of illustrate the general principles of looking beyond the minimal model of the standard model. And then in my last lecture, I'll make connections with what Anisha's going to tell you. Anisha's going to talk about setting up an effective field theory and the formalism of the effective field theory. But of course, you can think about the standard model that we know and love. It's just some effective low energy field theory and try to learn new stuff by looking at it in this new way. So again, comments, complaints, questions. My email is probably better than the Slack channel, although I will try to respond to Slack. Okay, so in the last decade, the particle physics world has just been completely different from when I was a student. It's just like, boom, it's different. We found the Higgs boson. Because before we found the Higgs boson, there were lots of models which explained the world without the Higgs. And in fact, as I'll tell you probably tomorrow, there are lots of reasons why a standard model Higgs is a lousy object and why it has all sorts of theoretical problems. And you know, it might not have been there, but we found it. And then we found that the standard model, everything works. I could show you plots up the wazoo of calculations, measurements, and they all agree. There's pretty much nothing that doesn't agree with the standard model. And this is weird. Everything really agrees. So the question is, how do we know where to go beyond this? And there's been a lot of soul searching in the particle physics community recently. A few years ago, the European community gathered together to think about their future beyond the LHC. And as many of you probably know, the recommendation was to build what's called a Higgs factory, a high-energy E plus E minus machine that would study all the properties of the Higgs. So that tells you that we really got to understand the Higgs boson, and we really have to understand, why would I spend umpteen billion dollars and umpteen years measuring everything there is to know about the Higgs? And this is a really serious question for your generation to answer. So what is it that we're missing? And at the moment, as we speak, the US community is undergoing what we call our snowmass process, where we gather together to make a plan for the US community. Where are we going? So how does the Higgs feed into our future studies? Okay, so before I start talking about the Higgs, let me talk about the possibilities, I say for the future, but it's really for your future. It's not for my future, it's for your future, because these are very, very long-term projects we're talking about. So at the moment, we have the High-luminosity LHC. I'm looking for a stick or some kind of pointer. Okay, well, we have the High-luminosity LHC, which is the top line here. Proton-proton collider at 14 TeV. There are no plans to upgrade the energy of the LHC. So 14 TeV is what we have. But there are plans to run it longer and longer. And you'll notice on the far right there, it says 6 inverse attobarns. So that's really the 20-year plan. The plans that we had a few years back were 3 inverse attobarns. But we can just keep running forever until the detectors fall apart. So that's the 20-year plan. That's maybe your 10-year plans, shall we say. You guys are mid-career scientists at that point. I'm retired. And then there's a whole host of E plus E minus machines. There's the ILC, which is an E plus E minus machine that we've been talking about for 20 years, 30 years, a very long time. And the ILC would run at 250 GeV. And as I talk about the Higgs, you'll see that this is not a random energy, but 250 GeV is the energy where you get the best Higgs measurements. And you'll see that. I'll show you plots of cross-sections that says, aha, that's the right energy. But then you see that the ILC is predicted to step through energies. So the next energy is 350 GeV. So anybody want to tell me why that's good? What's special about 350? Yes, you can make 2 tops, right? The top mass is 175. So after we've measured everything we want to know about the Higgs, then we'll go to 350, and then we'll measure the... Okay. And then we'll measure the TT bar, and then we'll keep going to 500 GeV and a TeV to higher energies. And you'll see the next machine, Click, is proposed to go up to 3 TeV in E plus E minus. CEPC is a Chinese E plus E minus machine. And finally, there's a Muon collider here. This would run on the Higgs resonance to start to measure Higgs couplings, and then perhaps go to higher energies. So we've got a whole lot of plans for machines which are designed just to measure Higgs properties. Yes?
Why is it only 0.2 inverse attobarns at the TT bar threshold?
Oh, because, okay, that's a good question. You measure the Higgs couplings with a lot of luminosity, right? Because you want the Higgs couplings really precisely, because BSM models are going to predict that maybe the Higgs coupling to B's is a little bit different. So you need a lot of luminosity. 0.2 is just enough to do a threshold scan and get the top quark mass very precisely. So that's all you need for the top mass. You can see here that the different machines, they keep changing the luminosity depending on, some projected desires. I mean, I don't think this is fixed in stone. Okay, so it's up to us to define these physics cases. Okay, so here we go. The pretty pictures of finding the Higgs. Here's the discovery announcement. You've all seen this. This is an Atlas display, Peter Higgs. So we found the Higgs boson a decade ago, and everything we know about the Higgs is kind of standard model-like. So we have to ask, why is the Higgs boson so important? And the reason it's so important is because we have the standard model. It's important because we have the standard model, which is well understood and well defined, and as I said, well supported experimentally. So we've got the standard model with the quarks and the doublets here, up, down, charm, strange, top, bottom. We've got the leptons here. We've got the force carriers over here and the Higgs. But this model, as I'm going to claim in the next few lectures, leaves a lot of things unexplained, and it makes absolutely no sense without the Higgs. If you remove the Higgs from your model, it doesn't make sense. So let's start with doing some physics here, enough background. So here's a really simple example of electroweak symmetry breaking. We notice there are 4 force carriers. There's a photon, there's a gluon, there's a W, and the Z. And the photon, we know that its mass is 0 very, very precisely. They measure properties of light coming from the sun. So its mass is 0. We know the gluon mass is 0, not as precisely as the photon mass, but we know it's 0. So the question is, why are the W and Z masses not 0? So let's start with a simple example, a U1 gauge theory with a single spin 1 gauge field, which I'll call L. And this is quantum electrodynamics. So the Lagrangian is just F mu nu, and here we have F mu nu. It's just the covariant derivative here. So this has what we call a local gauge invariance. So I can make a transformation on my gauge field, shifting it by the derivative of any function, d mu a to x. So that's fine. So my theory has this gauge invariance. But if I wanted to add a mass term, is this distracting when I go back and forth? It probably is, right? Yeah, you're saying yes. OK. I'll pick one side. I'll pick this side today and that side tomorrow. So a mass term for the A, for the photon, would be m squared a mu. So you know already that if I add a mass term, it violates gauge invariance. Bingo, I can't have a mass term for my gauge fields. So we understand why the photon is 0. So the whole basis of our theory is going to be gauge invariance. Our theory has to be gauge invariant. So we cannot add a mass term for the W and Z because it would violate our gauge invariance.
What about Stuckelberg?
What about what?
Stuckelberg masses.
That's another story. We could talk about that one later. Sorry, but yeah, that would derail me. So we can add a scalar field phi with this charge E to the theory, and we can still have gauge invariance. So we have the same theory with our scalar field. So we just have d mu phi minus some potential. And we'll write down the most general potential. So this is just a U1 theory. So my most general potential is mu squared phi squared lambda phi to the 4th. It's got this covariant derivative. And again, the theory is invariant under these local U1 transformations. So I can transform A by a derivative and phi by a phase here. And it's instructive to actually do this with the Mathematica code and see that this construction preserves gauge invariance. So here we go. We have the most general thing we can write down that's invariant under these local U1 transformations. But what happens when we do this? Well, I've got 2 cases. I've got this mu squared, the mu squared and the potential, positive. So here's my potential. It's just a quadratic equation here, mu squared phi squared lambda phi to the 4th. And by convention, we'll take lambda to be positive. So this is just quantum electrodynamics with a massless photon and a scalar field mu. So when this happens, there's nothing particularly interesting that happens. But what if for some reason mu squared were negative? And I'm going to say we just postulate this. I wrote down here, why is mu squared less than 0? Well, supersymmetric models can kind of explain this. But in general, we don't have a clue why mu squared is less than 0. But if it is less than 0, something deep and profound happens. If this term here, where I put the absolute values just to remind us, if this term here has a minus sign here, then the potential looks like this. And physical states always have their minimum energy at 0. That's just quantum mechanics. So the minimum energy state is not at phi equals 0, but it's at phi equals v over square root of 2. And this is the definition of v, so minus mu squared over 2 lambda. And why is there a square root of 2 there? And it's just to screw you up. It's just to confuse you. It's put in by hand. It has no physics in it whatsoever. But this square root of 2 is here by definition, by convention. It used to be sometimes people went back and forth, but now everybody does it this way. So the physical particle has its minimum energy state at 0. It's right here. So the physical particle, I'll call it h, is just v plus h. We'll redefine our scalar field to shift it away so h has its minimum at 0. And then the other dimension of our complex field I'll call chi, and I'll just put it in a phase. So chi and h are the 2 degrees of freedom of the complex scalar field. So we've got a physical scalar, and we've got this thing chi. And of course, you all think, well, this is trivial. She hasn't done anything at all, right? All I did was say, the mu squared is negative, and I did a little bit of algebra. But what happens is truly amazing, and this is the miracle of electroweak symmetry breaking. So you just go put in this phi field into your potential and do your algebra. And what happens? You've still got your gauge fields, but now you've got a term E squared, V squared, A mu. So because of this spontaneous symmetry breaking, you have generated a mass for the photon field. So here we go. Here's a mass. And the mass is predicted in terms of this parameter V. So it's E squared, V squared over 2. And then just do an algebra, no trickery here. We have the Higgs field, d mu h, d mu h. So this has a kinetic energy term here, so it's a propagating field. It has a mass term here with the correct sign, so it's a scalar field with mass squared minus 2 mu squared. Remember, mu squared is negative. It's got this massless scalar field chi, which is what we call the Goldstone boson. So these chi interactions are gauge dependent. And what do I mean by that? Look at this term here. This is a funky term. It mixes the photon field with this Goldstone boson field. So we can redefine the A field to what we say gauge away the chi field. So if I redefine the A field, I can get rid of this term so that I don't have this mixed propagator. Okay? So this is the end of this simple example here. So we'll remove this mixed propagator here by shifting the gauge field like this with the d mu chi. And when I do this, the chi field disappears. And we say that it's been eaten to give the photon mass. That's the standard terminology. But it's really just a gauge transformation, a redefinition of my scalar field. And so this is what's called the abelian Higgs mechanism. And so this gauge has only physical states. So the Lagrangian has a scalar field, which is an F mu nu. It's got the mass term for the photon, here we go, and it's got a propagating Higgs field. And you can work out the potential just by algebra. So any questions before I continue? Yeah?
So what do you think you mean by a propagating field?
I mean it has d mu h, d mu h. It's got the correct kinetic energy term.
Okay.
Right. If it didn't have this term, it wouldn't propagate. I wouldn't be able to write it as a physical field. It would have no kinetic energy.
Sorry.
Yeah?
What do you mean there are only physical particles? Because there are some A's that have negative masses.
No, everything has a proper mass term. Or the signs of the mass terms are the correct signs. Yeah. That's what I mean. So you have this A field. It's got a mass term with the proper sign. I could go look for it as a physical thing. I've got the H, it's a physical thing. I've got the potential here, which is just algebra from back a few slides, and I can calculate its interactions. And that's it. So this is very nice. So this is spontaneous symmetry breaking. It comes from a non-zero VEV of a scalar field, and then results in the disappearance of the Goldstone boson and the transformation into the longitudinal component of a massive gauge boson. So what do I mean by that statement? So remember quantum electrodynamics, the photon. You know how many degrees of freedom a photon has, right? 2. Good. It's got 2 transverse degrees of freedom. It does not have a longitudinal degree of freedom. A massive gauge boson has a longitudinal degree of freedom. So when I give this A field a mass, it acquires a longitudinal degree of freedom. So all the exciting stuff about Higgs physics and spontaneous symmetry breaking, all the cool stuff is going to be in this longitudinal degree of freedom, which you didn't have without the spontaneous symmetry breaking. And then here's this caveat. You got to have mu squared less than 0. It all relies on this magic that this one term is negative. So as young scientists, you should continue to think about this problem which theorists have been thinking about for generations. Yeah?
So you said there are potential SUSY explanations for mu squared being less than 0?
Yeah, you want to hear them? So if you have a grand unified supersymmetric model, so way up at the Planck scale, you've got a model, and Gigi's an expert in this. I'll pin you. So if you have questions, you can ask her. But if you have a grand unified model at 10 to the 16th GeV or something, with a very small number of parameters in your supersymmetric model. Your supersymmetric model relates all sorts of different things. So then you evolve everything down to the weak scale. And Michael Dine did this in 1977 or something, years ago. You can show that mu becomes negative in these models as you evolve it down due to renormalization group running. So this simple supersymmetric model, which does this, is now ruled out experimentally. But it still was kind of a nice motivation that maybe there's something there. And actually, I should continue with that. When Michael Dine wrote this paper where he's evolving the supersymmetric parameters down and getting mu less than 0, it only works if the top quark is about 175 GeV. And this was way before they found the top quark. So that was actually something kind of cool, making you think that there might be something there. OK, let's see here. OK, so an aside on gauge fields, I made this transformation to get rid of the chi field. But this particular gauge is not very nice for calculations, because if I calculate the propagator of my A field, it's got these terms k mu over m squared. And terms which grow with energy are very bad from a theory point of view. I will show you later today or tomorrow that when you have effects growing with energy, you tend to violate what's called the unitarity bound. And such theories tend to run into trouble. So you can, of course, add gauge fixing terms to change your gauge. And the gauge we mostly use these days is called RC gauge, which is just making this transformation. Again, it's just putting it back and doing the algebra, which I strongly recommend that people do some algebra. And you get a term where the interactions of the two gauge fields here depend on the gauge shift, OK? So the propagators of the gauge bosons, which now I'm talking about an abelian model, but in a minute I'm going to tell you, well, we can do it for SU2 cross U1. The propagators of this massive gauge field depend on this gauge transformation property. So most of us know and love Feynman gauge. Feynman gauge has z equals 1, and it's just g mu nu for the propagator. So in Feynman gauge, the Goldstone bosons propagate, however. So if you're calculating something, you have to include the Goldstone bosons, which can be a pain. OK, so now let's talk about the real model. And I'll do this in 2 slides. OK, so in the standard, yes?
2 slides back where you have the Lagrange.
Yep.
At face value, one could say, I have a mass for the spin 1 particle, and I have a chi. So my degrees of freedom here are, say, 4.
Chi is not a degree of freedom, because chi is just a number. It's something we put in by hand. It's not a field. It's just free. I can pick it as I like. I could, if I felt like it, I could pick it to be 2/3. Like, you know, that wouldn't be convenient. But
I mean the field, like.
Oh, you mean this guy?
Yeah.
Yeah. So the counting is different. And in fact, when I do the counting, it's gauge dependent how you do the counting. Yeah. Right. Yes. I'll show you in a few minutes, and you'll say that I'm sliming you, because that's a very good point. But yeah. So you looked at my slides ahead of time? Yeah. Well, you could have really gotten me on this one, because there is a point. So Electroweak symmetry breaking. So now let's look at the real standard model with the Higgs. I'm going to put in a complex SU2 doublet. So my phi field has a phi plus and a phi 0. It's complex. So there are 2 degrees of freedom upstairs and 2 degrees of freedom downstairs. So there are 4 degrees of freedom in my phi field. So then I can write down the most general renormalizable SU2 cross U1 invariant scalar potential. So here's my potential, mu squared phi dagger phi plus lambda phi dagger phi squared. And this is exactly the same thing as I wrote down for the abelian Higgs model, other than the fact that the phi is now an SU2 doublet. So this mu squared, again, we'll take it to be negative, and I'll say, well, I don't know why, but if I take it to be negative, exactly the same thing happens as in the abelian model. Okay, and the minimum of the potential is here, h plus v over square root of 2. And now my Goldstone bosons, I'll call them omega here. So there are 3 of them. It's omega dot sigma. Sigma are the Pauli matrices. So I haven't cheated you on the degrees of freedom, because phi has 4 degrees of freedom, H has 1 degree of freedom, and the omega had 3 degrees of freedom here. I've tried very, very hard, I've probably been unsuccessful, to call the standard model Higgs capital H. You'll probably find places in my notes where it's not capital H, but I've really tried to make it always be capital H. Okay, so now we can do the same algebra as before, and I'm not going to do it. I'm just going to tell you the answer. I'm going to tell you that we have the potential. It's got 2 parameters, but now I can trade the mu squared and the lambda for v squared and the mass of the Higgs squared. Yes?
Thanks. You mentioned in your favorite models you had a scalar and another Higgs.
Mm-hmm.
Does that, when in models in which a second Higgs is added, does it always have to be a doublet, an SU2 doublet also?
No, absolutely not. It can be an SU2 singlet, in which case it doesn't do a whole lot. It can be an SU2 triplet, in which case there are tons of limits on it from consistency of the theory. It can be any representation of SU2. I wrote a paper with SU2 quadruplets, which is not very interesting, by the way. But no, it doesn't have to be a doublet. The doublets are the easiest and maybe the most motivated, but it doesn't have to be. No. Take your favorite representation, write a model, have some fun. And actually, that's one of the things you should get out of my lectures is that when you build a model with some new scalar, there are all these things you have to check to make sure it's a good model. And you know, it's formulaic. You got to check this unitarity, blah, blah, blah. So hopefully, by the end of my lectures, you'll have your checklist for my model. And most of the models you'll see are stringently limited at this point. Okay, so we minimize this potential. We solve for v squared in terms of mu squared and lambda. We multiply everything out during our algebra, and we get the potential. It's got a Higgs field with a mass. It's got a Higgs cubic term and a Higgs quartic term. And the really, really important thing to remember about the standard model is that these things are predicted. The trilinear couplings of the Higgs, which I've called lambda 3 here, are predicted in terms of mh squared over 2v. So you've probably heard the LHC talking about measuring the trilinear coupling. Well, in some sense, that's just crazy, because if it's not exactly mh squared over 2v, bingo, aha, right now you know it's not the standard model. These are absolute predictions, and there are no free parameters. And that's why it's such an amazing model, is because you are not free to adjust anything. You've got the Higgs mass, and you've got v. And that is it, guys. So it's a very, very simple model. OK, so now questions? OK, so a little bit of algebra here. I'm not going to work it out because it's simple. You can couple the gauge bosons to the SU2 doublet. So now I have a covariant derivative, which I've written down here. It's exactly like the one I wrote down for the coupling of the photon, d mu minus IEA. So here, G is the SU2 coupling, G prime is the U1 coupling, B is the U1 gauge boson, and unfortunately, WI is the SU2 gauge boson. And this is historical, the way people do this stuff. W mu A, these are SU2 gauge bosons, so they are not the physical W bosons. Sometimes you might use a different script or something for them, but it's confusing, I think, because these are the SU2 bosons, or the SU2 gauge bosons that couple. So here we go. So we write down d mu phi with the covariant derivative, and you can get the mass terms. So let's see here, d mu phi. So the phi has a 1 over the square root of 2, which goes to 1/2, and then you've got these guys squared, so that's the 8th, from 2 d mu's and from 2 1 over square roots of 2. And here's the v. I just wrote down the v in the phi field. Here's the v, and here are the 2 covariant derivatives. Okay, so you multiply this thing out, and you've got g squared w1 squared, g squared w2 squared, and then another combination here. So this combination here is going to get a mass and be the physical mass of W boson. And this combination here is going to get a mass proportional to V squared and be the physical Z boson. And again, let me state the really important thing. There are no free parameters here. There are no free parameters. These couplings, they're absolutely fixed by gauge invariance. OK, so here's just some algebra. You get the W mass and the Z mass just from there. So the W mass is the SU2 coupling times V over 2. The Z mass is the SU2 U1 coupling V over 2. So the masses are proportional to the VEV and to the gauge couplings. And so the orthogonal coupling to the Z is the photon, and it's massless. So here we go. So we started out with 2 parameters in the Higgs potential, and now we've got 2 gauge parameters, and that's it. This is standard model. So we can go through and write the couplings to everything. So here are the couplings to gauge bosons, written one way. Okay, so the W's, the physical W's coupled to the Higgs, proportional to the SU2 coupling and the mass. So here's the mass. And the Z's coupled proportional to the gauge coupling, the mass. And cos theta W is just the ratio of the masses here. So it's nothing deep and profound. It's just the ratio of the masses. So the spontaneous symmetry breaking gives the W and Z a mass. And again, it gives them longitudinal polarizations, which, as we'll see, gives us all the physics. And again, there's no free parameter in the couplings. So when you look at the limits on the couplings of the Higgs to the W and the couplings of the Higgs to the Z, well, if it's not exactly 1, it's new physics. Okay, so here's the counting for you. I'm going back to unitary gauge, which is the only gauge that you can really do this in, because unitary gauge has no Goldstone bosons. So we started, what, 4 massless gauge bosons, the SU2 and the U1 gauge bosons. So they only had transverse polarizations because they were massless. We had a complex scalar doublet, which has 4 degrees of freedom, aka 12 degrees of freedom. So after the spontaneous symmetry breaking, we have 3 massive gauge bosons, the W and Z, and they each have 3 polarizations, 2 transverse, 1 longitudinal. So they're 9 degrees of freedom. We have a massless photon, which is 2 transverse degrees of freedom, and a physical scalar. So in unitary gauge, you can do the simplistic counting where the degrees of freedom are preserved. This kind of simplistic counting only works in unitary gauge. But you can see what's happened is you've changed degrees of freedom from your scalar field to the transverse, or to the longitudinal polarizations of the gauge bosons. Okay, so far our model has no fermions, so it's not very interesting. Well, way back when, in Fermi, we had a structure of how 4 fermions interacted. So we had that the fermions interacted through couplings, or leptonic currents here, we'll call them. And these currents were just the couplings of the electron to the neutrino, muon to the neutrino. And by explicit measurement way back in the day, we knew that the fermions, or the leptons, only coupled to the weak interactions by left-handed couplings, 1 minus gamma 5 over 2. So only the left-handed fermions felt the charge-weak interactions. So you have muon decay, you measure the electron coming out. So the only things you can measure are the energy spectrum of the electron at different angles. So by measuring this, we induced that it was left-handed, 1 minus gamma 5. And this has been known for a long time. So when it came time to put fermions into the standard model, we just made an assumption. We made nonsense. We said, yeah?
I think this is probably pretty obvious, but could you explain again how muon decay tells us that you can only couple to left-handed particles?
Oh, yeah, that's not so obvious. That's a really good question. In fact, there are tons of theory papers. So you would make an ansatz. You would say, maybe it couples A times 1 minus gamma 5 plus strength B times 1 plus gamma 5 plus strength C times a scalar coupling like that. And then you do tons of measurements. And you would see that this is what came out. Okay. So it's an experimentally inferred thing. So no, it's not obvious.
So 16, you write 16 coefficients out in
Yeah, they used to measure these things. There are a whole lot of old-time experiments measuring these. Yeah. So then we say, aha, we're going to construct our model of weak interactions exactly the same way. So we're going to put everything that talks to the weak interactions into a left-handed doublet. So here are the quarks, up, down, left, and the neutrino and the electron left. So here they are. So we'll, by ansatz, say that they talk to the weak interactions. So they will be SU2 doublets, and then we'll assume that the other guys are SU2 singlets. So this is put in by hand. So we've put in 5 multiplets here, 1, 2, 3, 4, 5, for each of the generations. And except for the masses, all the generations are identical. So if we didn't have any masses or interactions of the fermions, we would have a U3 to the 5th symmetry. So we had 5 multiplets. Okay, we put them in by hand. But now something kind of interesting happens. So the fermion couplings to the gauge bosons are again fixed. There are no free parameters. So the left-handed doublets couple with an gauge covariant derivative d mu here, and the right-handed singlets couple with the gauge covariant derivative d mu. So I just wrote down what it is here. So this is color, which only acts on the quarks. These are the gauge interactions. So T plus, T minus are combinations of the Pauli matrices. T3 is a Pauli matrix. So these guys, the T's, only act on the left-handed guys, and the other guys act on the right-handed guys. So it's fixed. Oops. So now we can go back to our theory of muon decay, and we can learn one more thing. We can learn that if I'm looking at, I put here nu e goes to mu nu just to make it easier. It's the same interaction. So in the Fermi theory, the interactions of the muon, the electron, and the neutrinos would have the left-handed structure with a 2 square root of 2 G Fermi here, and that defines the strength of G Fermi. That's just put in. But now I can calculate this in my Electroweak theory, because now I've postulated that my leptons interact via the weak interactions here. So we've got the muon with the neutrino, so it's G over square root of 2 and the 1 minus gamma 5 at the vertex, and then there's a propagator here, k squared minus mw squared. So now for muon decay, the momentum k is much, much less than mw. So these two things are supposed to give us the same answer. So if k is very small, we've got this side, 2 square root of 2 G Fermi equals this side, G squared over 2 mw squared. So by matching them up, we see that this parameter v, the VEV of the scalar field, is not a free parameter. It's fixed by muon decay. In particular, 1 over square root of 2 v squared is G Fermi. So v squared is 246 GeV. So here's our first example of an effective theory. So the effective theory is the Fermi theory, which reproduces the exact high energy theory of the SU2 cross U1 theory. So by making this matching, what we've done is we've reduced our number of parameters even further. So now we've, yeah.
From a historical point of view, we knew GF already. So,
Yeah, we did.
So then why didn't we know where the Higgs mass would be if we knew what the VEV would be?
But this doesn't tell us what the Higgs mass is. It just tells us what V is. And that's a really good question. Let me go back. I think I have the formula here. That's why I like slides, even though I know they're not good. But no, I didn't write down that formula. Okay. The Higgs mass is still a free parameter. So by the counting in the scalar potential, I had mu squared and I had lambda 5/4. Okay? So then I'm going to change that mu squared and the lambda for G Fermi and M Higgs. So M Higgs is still a free parameter in my theory. But it's only got one free parameter now. Okay. Yeah.
Actually, question about that. So, isn't the VEV technically also a free parameter, just very tightly constrained, since that's an approximation to say that it's proportional to G Fermi?
It's not an approximation. It's the matching of the weak interactions to our gauge theory. So it really is fixed, because our gauge theory has to reproduce the weak interactions.
But wouldn't it only work for k equals 0?
Well, the mass of the muon is really much, much less than 80 GeV.
Sure.
You know, so it's pretty exact. Yeah. So let's see what time. This is one more miracle of the standard model, which you have to appreciate that this stuff is really miraculous the way it comes out. So we want the fermions to have a mass. We know the B quark isn't massive. You might think maybe the up quark was massless, but you know the B is pretty heavy. The top is pretty heavy. So our theory has to accommodate fermion masses. So what if I try to just add a fermion mass to my theory? So I would add a mass m psi bar psi. Well, you can't do it the way we've constructed the theory, because the left-handed particles are SU2 doublets and the right-handed particles are SU2 singlets. So a mass term would couple left-handed particles with right-handed particles. So I am not allowed to add a mass term, again, by this requirement of gauge invariance. So gauge invariance, SU2 cross U1 gauge invariance, does not let me write a mass term for the fermions. But aha, we've got the Higgs here. The Higgs is an SU2 doublet. The left-handed fermions are SU2 doublets, so I can construct a gauge invariant object out of these two SU2 quantities. So I can construct an interaction sidebar left. So this is my up-down doublet, SU2 doublet. Phi is an SU2 doublet, so the indices work out here. And D is a right-handed singlet. So this guy can give me a mass term for my fermions. So what it does is it takes the down component of the left-handed guy here, talks to the down component of the phi, which has a V in it, and the right-handed down quark. So you have, here's V plus H downstairs from the phi, and here's the SU2 doublet, and here's the right-handed guy. So it gives me a term, which is D bar V D. So it gives me a mass term. So that's good, and that's fine. The phi tilde there is I sigma 2 times phi, which is also an SU2 invariant, which just makes it so that we have V plus H upstairs, so we can give the top quark mass. So now this is great. We can give everything a mass. And so this Yukawa coupling in front here is proportional to the mass. So the Higgs couplings to the fermions are proportional to the mass. So now I've just done this simple example with one fermion, but if I wanted to, yeah?
So up there with forbidden by SU2 cross U1, that's pretty straightforward. But once you've broken SU2, what here is specifically fixing the masses to the Yukawa couplings, other than the I mean, why can't we just add in extra terms and have those be incredibly tiny, or have massless up quarks?
Well, we need a gauge symmetry, so we're going to start with our gauge symmetry. So everything is going to start with a gauge symmetric theory. So we're not going to add in anything else in a broken phase. We're going to say I'm starting with my gauge symmetry, and that's it. That's my model. And in that context where that's my model and that's it, I can't add anything else.
Well, after this is broken, what's stopping you from just changing the...
In a U1, after it's broken, we have a U1 gauge theory, right? And in a U1 gauge theory, even so, these guys have different U1, well, I guess they have similar charges. But you want to just add it in quantum electrodynamics.
He wants to break the gauge invariance by explicitly adding.
Yeah.
It's spontaneously broken, but it's not explicitly broken. So we're still not adding terms that explicitly.
Right, that's what I'm trying. We're only doing a spontaneously broken theory. That's our theory.
Okay, so
Yeah.
that's just like...
That's our theory. It's a spontaneously broken gauge theory. Yeah. Yeah, it's bad if you do that.
The specific part that I'm asking about is like, why are the masses fixed to the Yukawas? Because, I mean, I know that massless up quarks have some appeal in where they can...
That's another discussion. Let's save that for discussion, period. Yeah. Well, I mean, there's no problem in this construction of having a massless up quark, right? It wouldn't couple to the Higgs. So suppose I said that there were some generation indices here. I had generations 1, 2, 3, say, and then I had to diagonalize my mass matrix. See, I didn't put that. So when I diagonalize the mass matrix, I'm also diagonalizing the Higgs couplings. So there are no off-diagonal couplings to the Higgs. So this mass Yukawa connection is very special to the standard model. So the Higgs always couples proportionally to mass. So for example, if I measure the rate that the Higgs goes to B's normalized to the rate that the Higgs goes to taus, well, there's a factor of 3 because the B has color, and it's just the ratio of masses. And this kind of relationship has been verified experimentally. So suppose the standard model weren't everything. Suppose there was some physics out there that I didn't have. So suppose I'm going to add a term to my Lagrangian, which has the doublets, Q left, here's the Higgs, the right-handed guys, where these are generation indices, IJ 1, 2, 3. And it's got some matrix Cij. So then the Yukawas would be the mass terms as before, but then there'd be this extra piece from this term I added. And in general, I can't diagonalize these things simultaneously. And so the mass and the Yukawas are no longer proportional, and then you get things like Higgs goes to mu tau. And this happens if I just blindly construct, for example, a 2 Higgs doublet model, and I don't pay attention to the fact that I don't want interactions like this. So,
Sorry, is it sufficient to just have Cij commute with the Yukawas?
what do you mean? What do you mean by commute?
Diagonalization is your worry.
Well, you could construct Cij in such a way that it could be simultaneously diagonalized, sure. But in general, you can get flavor changing neutral currents unless you pay attention. Yeah?
Are flavor changing Higgs decays completely ruled out, or is there some little bit of room?
Well, I'm glad you asked that, because here's the plot. Okay, because yeah, people look for flavor changing Higgs decays. They look for things like Higgs goes to mu e or Higgs goes to mu tau. I mean, there are a lot of plots that I could show you from the LHC. But yeah, people really want to look for this. And what's interesting about this is the limit from the LHC is this dashed line here. So these are off-diagonal Yukawa couplings. And what you learn from this is that if you want to look for these flavor-violating Higgs decays, you're really going to do better if you look for things like mu to 3e, or here's mu to e gamma down here. So precision experiments which are honed in for looking for these specific things are a better place to look for these guys. And of course, they're not completely ruled out. They can certainly exist at very small levels. Okay. Yeah? Oh, that's a theory bound, and that's the Yassine bound. It's a theory bound saying that you don't expect these couplings to be too big. They kind of make a fudge factor that the couplings are sort of proportional to the masses in a scale. It's not a rigorous bound. It's one theory thought.
I'm sorry, I'm having trouble doing this plot. So the blue curve is observed. What is being?
It's the observed limit. Yes. So it's the observed exclusion region. Yeah, good point. Yeah, if we had found this, well, you would know it. You'd probably be reading it in the New York Times if we'd found flavor-violating Higgs decays. And in fact, if we had found flavor-violating Higgs decays at the LHC, you might say you didn't need to do these things because we'd already found it, but no such luck. So I didn't say anything about neutrinos. By construction, we don't put neutrinos into our standard model. And this is purely by construction. It's purely an assumption. I could have put them in. I could have said, well, let's just have some right-handed neutrinos the same way as we have right-handed down quarks and right-handed electrons and right-handed other stuff. There's no theory reason why I couldn't have just done that. In fact, some people do. So you just write the mass term connecting the lepton doublet with the right-handed neutrinos. Bingo, it's the same as always. The thing is that neutrinos are different. Since they have no quantum numbers, we can also add a mass term, which is a right-handed guy, a Majorana interaction. And so then you have two sources of masses for the neutrinos, and it becomes very, very interesting constructing the mass terms for the neutrinos. So you get this rich mixing phenomenology with the Majorana mass terms and the Dirac mass terms. So that's all I'm going to say about it, but it's actually kind of interesting working it out. But it's very, very different than the quarks just because of the possibility of adding this Majorana mass term. Okay, so let's just review this here. I've talked about the couplings to the fermions are proportional to the mass. The couplings to the gauge bosons. Here I wrote mass squared, and that's because it's mw squared over v. Sometimes I might write it as gmw. You can go back and forth with these, right? Because I know mw is gv over 2, so take your pick. The gauge bosons don't couple to the Higgs at tree level, the massless guys, because the Higgs couples to masses. So the gauge bosons couple at one loop to the gluons, to the photons, and a mixed term with a photon and Z. And I've written it this way just because these functions out front are normalized such that they go to 1 when the stuff inside goes to infinite mass. But you can see that the Higgs will couple to gluons at one loop, it'll couple to photons at one loop, and it'll couple to the photon and the Z. And this is a huge motivation for people who like to build models, because in particular, the coupling of the Higgs to the photon is pretty well measured. And so you can play with models where there's new charged stuff interacting in loops with the Higgs and try to learn something about it that way. Excuse me. Okay, and again, just for summary, the Higgs self-couplings are proportional to the mass squared of the Higgs. So in this whole big construction here, I've really only done 2 things. I've assumed that this mu squared parameter was negative. I've worked through all my algebra, and everything is fixed now except for the Higgs mass. So we have a theory which is full of predictions. Okay? Questions?
So here in this discussion, you only consider the tree level Higgs potential, so but Higgs potential will be identically collected.
Yeah.
So this V is.
I will show, I do have that later. Yeah. We'll get to that. Yes, because that's a good point. Because I've been tree level, yeah.
So you put a lot of emphasis on the fact that mu squared has to be negative. And that seems like a very classical picture to have.
Mm-hmm.
So, you know, I guess how prevalent are other models of Coleman-Weinberg-esque potentials where you can generate a bed maybe without something like mu squared?
Right. You still have to have this negative effect, though.
Okay.
Yeah. And in fact, I'll talk about the Higgs potential, tomorrow. Maybe tomorrow, maybe the next day. But yes. Because yes, this is a very classical picture, a spontaneously broken gauge symmetry. Yeah. Okay. So, simple and predictive. There we go.
Sorry, what was the last thing on your slide, the previous slide?
I don't know, what was it?
Just I.
Oh, the little footnote?
Yeah.
Well, there's some function in front of these things.
Oh, 1. It goes
I just normalized it so that those things are 1 when the stuff inside becomes very, very heavy. That's useful for various reasons, but it doesn't mean anything. It's just normalization. Because I didn't tell you what those functions were yet, right? So you write the standard model on a mug. Anybody want to tell me what's wrong with the standard model on the mug here?
It has 2 dimension conjugate.
Does it have 2? It's missing the psi bar here. Yeah, it's missing the psi bar, right? It's psi bar phi psi, which was pointed out to me recently. Okay. That's not my picture, but lots of people have those T-shirts, and it's wrong. So if you're buying the T-shirt, you're scamming people. Okay. So now we got this beautiful model. So yeah.
Sorry, a couple slides back, you said the only parameter left is unpredicted parameters MH.
Yeah, that's true.
Can you give an example where another parameter was predicted? I don't figure out how those unknown parameters reduce to just one unknown now.
Well, we started with the potential, which had 2 parameters, mu squared and lambda, right? Okay, and then we minimized it, and it's 2 parameters. But one of those parameters, V, we know from G Fermi, because we made the association of them. The other parameters are the weak coupling and the SU2 coupling, G and G prime, which have been measured in Z decays, for example. So they're very well known experimentally. So that's the point, is we've measured them experimentally. So if I calculate Z goes to BB bar, say, the LEP experiments measured that super precisely, so they know those couplings. So the only thing that we didn't know 10 years ago was this mass of the Higgs. We measured everything else. Yeah?
You mentioned like 15 minutes ago that measuring the trilinear coupling was something that people were using as experimental motivation, but we should already know it based on Higgs mass and V. The same is said for the quartic coupling then too?
Yeah.
Okay, so.
Yeah, the quartic coupling, oh, here it is. The quartic coupling is mh squared over 8v squared. And in fact, I don't know if I have it in my slides, but there are people who have ideas that maybe if we build a 100 TeV collider, we might maybe be able to measure the quartic coupling at 2 sigma. So not in your lifetime is the answer.
But I mean.
It's predicted.
Right, but I
So-
guess why are people so.
Why are they so excited?
Yeah, because we already know these parameters.
But we haven't measured them experimentally. Maybe this whole thing is just a load of hooey. I mean, we got this potential and we got this scheme, but maybe just, not the way it is, because, I mean, we don't have any experimental evidence that we have the potential exactly this way. So you got to measure at least the trilinear coupling to see that it came from this. Because if I had some other model, it might be a different coupling. For example, the 2 Higgs doublet model, the trilinear coupling of the Higgs is different. It's different in the Higgs singlet model. So this is only a prediction of the standard model. Yeah. Yes?
Since we're speaking to how well experiment has measured these things, what about Higgs couplings to anything below 3rd generation?
Oh, I'm coming to that. You're going to hear a lot about that. You're going to be bored with that. Well, maybe not. I think it's cool. But we're going to hear about why everything I say has been experimentally verified. Because to me, that's really important, that we just don't say stuff, but we actually have to see that that's what the experiments confirm. So how do we make a Higgs at a Hadron Collider? So 2 gluons, a fermion loop, and a Higgs. There are a lot of gluons at the LHC. So even though this is a loop diagram, it tends to be, well, it is the largest mechanism for producing a Higgs because there are a lot of gluons at the LHC. So in the loop is the top quark, the bottom quark, all of the fermions that we have run in the loop. But now we know that this coupling here of the Higgs to the fermions is proportional to the fermion mass. So it's really only the top quark that matters. The B contributes at about -4% of the top quark contribution. So this thing depends on new physics in the loop. If I had some new particle, if I built a supersymmetric model which had a stop quark, say, it would go in this loop too. So the production rate for glue goes to Higgs would depend on something that I don't know about. So that'd be great. It wouldn't come out the way I think it would. If we want to also look for this coupling of the top to the Higgs, because after all, it's the biggest coupling, we can look for glue goes to TT bar H. So here we go. Here's the coupling of the Higgs to the top quark. And here it's a cleaner measurement of the interactions of the top with the Higgs because it doesn't get messed up by this loop where there could be something new in the loop. And then we have the 2 processes which connect the Higgs to the gauge bosons. So this one here we call associated production. So it's QQ bar goes to WW Higgs, or QQ bar goes to Z Higgs. So this coupling here, the WWH coupling, is GMW. So it vanishes if V is 0. So if we didn't have the VEV, this thing would vanish. This is proportional to the same couplings, WWH, and we call this vector boson fusion, because it's as if the quark spit out a W and the quark spit out a W, and the 2 W's just fuse together to make a Higgs. So again, this interaction would vanish if V were 0. So these are the really important ways we make the Higgs. And here are the rates, and I just want to show this before I start talking about the individual things. So this is the mass of the Higgs. So these rates aren't very sensitive to what exactly the Higgs mass is. It's measured to be 125, but it doesn't really matter here. And here's the rates. And notice that this is a logarithmic scale. So here's the gluon fusion rate, and it's an order of magnitude above all the other ones. So all these down here are much, much smaller contributions. But what you should look at on this is the fine print on each of these lines, because each of these things are calculated to NNLO QCD plus NLO Electroweak. And this is a huge triumph of particle physics, that we can calculate these things to next to leading order. And I hope some of you are working on this, because in order to measure Higgs properties and to compare them with our theory, we need even further precision on our calculations. So once we've made the Higgs, how does it decay? Well, since the Higgs likes to couple to mass, it mostly decays to BB bar pairs. So this is the branching ratio. Again, notice that this is a logarithmic scale here. Okay, so here's the Higgs to BB bar. 3 orders of magnitude down here is the Higgs to 2 photons, and then there are a bunch of other Higgs things. So when you see WW here, you should turn your brain on and say, does that make sense? What's plotted here, right? Because the W mass is about 80 GeV, and the Higgs mass is 125. So what is plotted here is not really WW, can't be, right? Yeah.
So thinking about those QCD corrections, since QCD is not perturbative, who's to say they're any good?
What do you mean QCD is non-perturbative? These are calculated in the perturbative regime where the coupling constant is 0.118, and it's a perfectly well-defined perturbation theory. We calculate at PT above, I don't know, 10 GeV or someplace, but no, they're absolutely calculated in the perturbative regime.
Okay.
Yeah. We're not calculating like the lattice guys do at 1 GeV where the coupling is very, very big.
I guess actually I have a follow-up. Isn't the LHC running in the non-perturbative regime though?
What do you mean?
No, 13 TeV I guess is still within the perturbative regime.
I don't have a plot today, but I'll dig one up for you tomorrow, because what we're colliding at the LHC is the partons, the gluons and the quarks. So when we collide the gluons together to make a Higgs, the invariant mass of the 2 gluons is the Higgs mass, right? Because it's mostly produced on resonance. And at the scale MH equals 125, alpha S again is, I don't know, it's probably 0.11 or something. So it's perturbative, yeah. So, but let me continue with what WW means. Anybody know? I'll take comments. Yeah. Yeah, so really what it is one W on shell and the other W going to 2 fermions. So all those branching ratios are hidden in there.
So this is a 3-body decay that we're
Yeah.
Okay.
It's a shorthand for a 3-body decay. So for example, ZZ is clearer here. So I've got one Z, the Z is decaying to whatever, 2 leptons. So I know it's a Z because I measure those 2 leptons, I reconstruct their invariant mass. And then the other Z is going to all the fermions here. So yeah, this is kind of a shorthand way to show it. So it's a cheat. Okay, yeah?
I don't know if this is quite a well-posed question, but I'm a little curious about how the Higgs looks kinematically at kind of the end stages, when we actually detect it.
Oh, I'll show you that. That's coming. Yeah. I'm going to get more and more detailed, and I will show you that. And that will address the question about is it perturbative and so forth.
Wait, can you make a comment on why the branching ratios seem to go up for gauge bosons but down for the quarks, I guess, and the muons as you increase the Higgs mass?
Oh, well, it's because of this business of we're below threshold, right? Because we can't really make the 2 W's. So we're approaching the threshold for this. And so it's a 3-body decay versus a 2-body, basically. But I mean, we know the Higgs mass.
Yeah.
But it's the difference between 2 and 3.
So that means that the increase is mostly due to the increase of the phase space, the 3-body.
It's just different, right? I mean, they're spread out differently in phase space. And in fact, if you want to be really boring, I could calculate that for you. I like calculating stuff. Actually, it's not boring. I love calculating stuff. Just because I think you learn from it, how things are different. And in fact, what I'll do is add to my notes the reference to somebody who calculates this stuff in gory detail, because I think sometimes that's helpful. So I have just a few more minutes, so I'm going to show you some public relations slides because I think they're so cool. Just to show you where we've gone here. Because, as I said, the Higgs production, it's predicted. It's predicted in terms of the mass. And now it was discovered 10 years ago through ZZ star, the one we've just been talking about here, and gamma gamma. So even though the gamma gamma branching ratio is 10 to the minus 3, it was a discovery channel because it's so clean. It sticks out so much above the background. So where have we gone in the last decade? And so I think it's interesting to look at these. So this is the Higgs to gamma gamma spectrum. So you're looking for 2 photons. Now at the LHC, there are lots of photons floating around. You can make QQ bar goes to 2 photons. That's this whole thing falling down. And the Higgs is this little pimple here. So here was the discovery, and here we are 10 years later. But look at the difference in the scales. We've gone from 1,500 to now this is 10 to the third here. So we really have a lot more Higgs bosons to measure this kind of little bump here. And it's the same thing for looking for the Higgs to ZZ star, that in 2012 we had, 30 events? So this blue one here is the observed Higgs. And over here in 2022, we have 100 events. So we have smaller events and smaller uncertainties. Yeah?
These plots are not bothered about how you produce the Higgs.
Well, no, what they do is they add them all up. So in your Monte Carlo, you've got glue goes to Higgs, you've got glue goes to glue plus Higgs, you might have the other stuff, but the other stuff doesn't really matter because it's so much smaller. So no, I don't care how I make it. I put it in my Monte Carlo and out it comes.
Why
Yeah?
does the signal look much bigger for the heavier and non-physical things, the 150 and 190 on the plot on the left-hand side?
This guy, why would this signal have been bigger than this signal?
Right.
Well, the biggest background is from Z's. So the signal sticks out more from the Z's than it does here. Okay. And as I was advertised, there is nothing, sadly, nothing surprising in what we see at the LHC. So when we calculate all these cross sections, so here we go. Here's making a Higgs decaying to photons, to Z's. Here up here, we have the predictions and the data. It looks just right. The earlier data had larger uncertainty. See, the size of the error bar is larger. But it pretty much just looks exactly like what we think. So this is my last slide, I think, for today before I go on tomorrow. So we're really changing how we study Higgs physics because we now have more than discovery. We've got these precision measurements. We've taken our measurements and we've measured the coupling strength of the Higgs as a function of the particle mass, CMS atlas to be politically correct. This plot is logarithmic and this is linear. And we see that even on a linear scale, it looks like things are pretty much just like what we expected. And I have to say, again, if it's not one, it's new physics, period. That's it. So any deviation would signal new physics. So I'll stop here and I'll take questions. I'll be around all day for questions. Yes? Yeah, I've got that tomorrow. And I do have it, and it's cool, and I'm going to tell you that why. Did anybody here write a paper about this? I knew there would be people, right? And I'm going to tell you why the Higgs comes in. Yes, I definitely.
Also, can you give a comment about 6 years ago, about 750 GeV? The particle physics community is so different from that. When we find an only signal from 600 GeV, Muon scale.
I think that's a sociological question. Because of plots like this, we get super excited when we see something that looks like it might not be the standard model. That was the W mass from CDF. That was the 750 to 2 photons. You know, we really want there to be new physics. And so as soon as we see something that we think it's new physics, a lot of people are thinking about, well, what could it be? And so, like I said, one of the things that I think you should get out of these lectures here are the things you check when you're building your new model to explain something. Yeah?
I just didn't understand why the gauge degree of freedom counting is so hard when you have the Goldstone boson. What does that do?
Oh, you just have more. It looks like you have more degrees of freedom.
Why
If you,
is that like okay? Like
well, it's this counting is too simplistic.
okay.
It's just to sort of get in your mind that we had the scalar field and now we have longitudinal degrees of freedom. It's a simplistic argument, you know, nothing deep. Yeah. Yes?
I guess is there? We're pretty good. We're pretty sure about the Higgs mass being around where it's at roughly now, right?
It's measured to 1% precision.
Right. So.
So yeah, we're pretty sure. Yeah.
The reason I ask is mainly because there's also a very it's sitting at a very interesting place, right, in terms of 129 versus 1.
I have that in my lectures coming up. Yes, you'll see this. This comes with the Coleman-Weiberg potential and what does the whole thing mean. Yes, that is coming. Yes. Okay. Go ahead.
I run the branching ratio. The Higgs to gamma gamma was a higher branching ratio than Higgs to mu mu.
Yep.
And I guess with the Higgs to gamma gamma, you just have the top running through the loop, so you don't take too much of a hit. Is that what's happening?
No, the Higgs to gamma gamma, you have a top, but you also have a W. And there's a playoff. They have opposite signs. The point about Higgs to gamma gamma is that the background is easier to deal with than Higgs to mu mu. So it's all about signal and background. So if you can't look at the branching ratios and say, this is bigger than that. You have to look at the signal and the background together.
And is there a good way that we know that this gamma gamma is Higgs and not some exotic meson or something?
Sure, because you measure 2 photons, you get their invariant mass, and it's 125.
Right, but it could be something else that decays to 2 photons that we don't know about.
But then you wouldn't get that the invariant mass was 125 GeV.
But if this thing weighed 120.
But
No, I'm saying.
Are you're saying is the Higgs something else?
Yes.
Could the Higgs be? Well, we know that this 125 GeV object decays to WZ's bottoms exactly like we think. We've measured its spin parity very precisely, so we know it's 0 plus plus. For me, that defines a Higgs.
Gotcha.
Yeah, right. Yeah. Okay, one more question, then it's coffee time. Yes?
So it seems like most of the things to be done in Higgs is like precision physics at this point. Is it?
Yes.
So is the LHC better there, or like a E plus E minus collider that you mentioned before?
I will show you that, but the E plus E minus colliders can get very much more precise measurements than the LHC. But the LHC is not so much worse than the E plus E minus colliders, because remember, the LHC is going to run till you have tenure. So they're going to get a lot of data, so the square root of n is going to be small. Whereas the E plus E minus colliders won't start until, I'm dead and buried. So, the projections are not so different. It's a question of timescales.
But is there something one can do that the other cannot?
Yes. And I will talk about this coming up, and it's a measurement of the Higgs width without making a lot of assumptions. Because I'll put this up before we stop. You will see by peering at the scale here that the Higgs width is extremely narrow. And in fact, it's narrower than the resolution of the detectors. So the LHC has to be extremely clever to measure this. Okay, we'll stop. You can get me a coffee break. Ethan? He's got something to say. I ended on time. I want my gold star.
We're perfectly on time, actually. The coffee's still getting set up, so I'll take another minute. So I didn't make an announcement earlier about the COVID policy. I announced it all by email. The policy as an option for your comfort level. The one thing we are going to encourage you to do is try to take the coffee breaks outside, just because we're right next to the outside door. It's very beautiful today. So the coffee will be set up right outside the right door, and you can go ahead and take it outside and go on. We'll reconvene in about half an hour.
Actually, I just want to clarify my first question. We have something like this. I was just trying to say that A0 at the
But that, well, that's really not physical, because, I mean, we've got this gauge boson, and that's its mass.
Right.
So I would measure the transverse and the longitudinal guys by their interactions.
Right. Right.
So this is not a physical question, is my point.
Right. Right.
Right.
Yeah.
Yeah. So.
Okay, just because I thought you might want to say something like, so I can write down the assumption for all fields have the physical side of this number.
No, I mean, this is the mass term.
Okay.
Yeah.
Okay.
Right. But I'll go through, if I get to it, I have an example where I go through the couplings, and that's the point, is how they couple.
Yeah, I mean,
yeah.
I'm sure there are plenty of examples. For example, in string theory, you have all these, because your space time is down, and then you have the time component, and then you have the spatial component.
Right, so it depends what question you're asking.
Right, yeah. Because in string theory, there are ways to get rid of this unphysical degrees of freedom before you even do any calculations.
Right.
Something like cone gauge fixing or something.
Oh yeah, you can do all this thing in light cone. I can't do it, but other people can do it in light
So, I mean,
cone.
there are probably like similar methods where you can apply to this situation.
But all that would come out from a physical point of view is interactions and cross sections.
Right.
I mean, so.
But then, I mean, if you have the wrong sign for the mass, then you have to write down the operators that has the wrong sign for.
Then you would have to, yeah, light cone is funky, yeah. But, yeah, you could do it.
Okay, sorry.
That's okay. Go ahead.
Yeah. I'm a little bit confused about this gauge one.
Yeah?
Right, yeah,
So
I'm just wondering.
We're starting with PP.
I mean, you can
and
further gauge fix until you have like no unphysical.
No. Oh, I got to show the PDF thing tomorrow.
Okay.
Because we're not colliding the protons, we're colliding the quarks and gluons within the proton.
That's
Right.
why I'm a little bit confused. Like here is H, here is TS. So the charges seem to be a little bit different. So, okay.
No, so it's, you've got the proton, then you've got a spectrum of Q bar interactions and blue interactions.
I see.
Yeah.
So these are the constituents colliding and producing something.
Well, so this is what happens when you have the two protons collide. But what's happening inside is it's quarks and gluons. Yeah.
You don't necessarily have to get rid of. But
Yeah.
Hi, I just wanted to introduce myself. I'm Ann Catherine.
I don't.
I totally understand.
I stay away from people.
Well, I mean,
You're Tim's student.
okay, so
I am Tim's student.
Good.
Yes, it's so nice to meet you, and I wanted to thank you for answering all my questions. I know
No,
I asked
I
a lot,
love
so
questions. Questions are good because, you know, everybody learns something from questions.
Right. No, but
Absolutely.
you're
Yeah.
saying that there
Everybody
are,
should
you're
ask
starting
questions.
with
You guys
3
should ask,
instead,
ask more
like
questions.
for any
I don't have to
vector
get through
boson,
all
we are
this.
starting with 3 instead
Gotcha.
of 4.
Well,
and I'm
thank
saying
you.
that
And looking forward to your
fourth, isn't
future
that just an expression
Good.
of Poincare invariance required on your?
Go ahead.
right. I mean, but you only need it.
I'm reading your name. Yeah.
Like, it's
So
not
I think the
physical,
mark
like,
is
it's
correct.
never anything you measure.
Oh,
If you,
Like, it's in the Lagrangian,
yeah, so if
but
you
you
write
never really
everything as like,
measure.
let's say,
You're probably more
left-handed
familiar with
view,
since you're
so like
from
if
the
you're using
amplitudes.
way notation.
Actually, I wanted to ask you about it
And the
because,
bottom one
like,
is like contracting psi with
I mean,
psi.
say I'm not
Okay,
smart
so you're
enough to
saying,
figure
yeah,
out
it's
unitary
notation.
how do I count?
Yeah.
And of course, since we didn't
Well, it's
define
mixing
these,
Dirac and
Goldstones are
Weil,
just
I guess.
kind of,
So you can use the bar. if
they're
it's
just
everything
coordinates
that's
on your
right
actual
next to
group,
psi.
so
And then the bar
they're
is
very
still
much
psi would give
Lie-valued
you- still
fields.
give you
They're
left
not
bar.
physical space-time.
Yeah, I just
Yeah.
saw people
They
conventionally
don't
use
actually
dagger
have
if you
like
use Weil
well-defined
notations.
like
yeah, it's just,
space-time values.
yeah, it's,
They're all
But yeah.
yeah,
It will
you need
work
all the
better.
fine print there.
Yeah.
But I think
And I
it's-
also
Say
thought
I
maybe
know
for
how
the
to
sorry.
Yeah, no,
Yeah.
go.
For the Yukawa, I think when we had the psi bar for the
I'm actually
Higgs
not
field,
so
we were missing
concerned
an epsilon
about the
matrix.
degrees of freedom in
Not the way I wrote it.
because you know
Psi bar
many of those
left,
are actually
phi.
We had
not
Q, we had Q bar and then H
Right,
bar
right.
for the
I know how
How
to
to
do
make
that,
high
right?
energy scattering.
As you say,
High
you
energy
can write this in different ways.
How you eliminate
You can write these in
that,
different ways.
because you, under the Goldstone theorem, you would essentially
You
see the
don't need
mean
the
of
epsilon.
the
No.
components being
This is right.
exactly mirrored by these
I
things.
forgot
They
to
should have exactly
This guy.